Hi everybody, today we're going to do volumes when we're going to shift around a different axis than for instance the y-axis and the x-axis. And we'll go over a couple of examples, just basic ones, so you guys can get the idea. So when we talked about these before, the idea is that when we're making volumes, we're taking some type of curve. Let's say this is x squared. And we're going to rotate this around the x-axis. And by rotating it, it spins around and gives us this shape that kind of looks like a funnel. Or this could be a cylinder or whatever shape we end up with when we spin it around. And our goal is to calculate the volume of this spun shape. And this is one of the easiest ways for us to start off talking about using integrals and finding volumes by just simply rotating it, because it gives us a basic shape. And the shapes are just circles. And we said before that we're just adding up slices of circles together. And as we add up the slices of circles, we end up with this 3D object here. It's just really just circles. And we're going to add up all these circles together to form a solid. And the calculus behind this was a simple volume is equal to pi integral from a to b of our function f of x. We're going to square it because that's our radius, and then we add a little bit of dx for a little bit of width. And this really is just a circle, which is pi r squared. And we're going to multiply it by a little bit of width, a little bit of depth here. So we can say this is almost like our height, or let's say width. Add a little bit of dx. So if we look at this in a spun a different version, we have a circle and we're giving it a little bit of dx, a little bit of height. And that gives us our volume measurement. Okay, this is our pi r squared. And we're raising it up by a little bit of dx. And as we stack these objects together, as we stack them up objects together, we end up with a solid here, as we see on our left. So let's go ahead and do our problem here. Let's go ahead and find the volume of this equation y equals x squared from 0 to 1. So the volume equation is pi integral from 0 to 1 of r squared, which is our function, because that's really our x. Sorry, that's really our y value here. See, from here to here, that's really my radius. And this radius is going to change for me as we go across the problem. And we're going to write x squared. We're going to square that. See, this is my pi r squared. That's just the circles. And we're going to multiply that by a little bit of dx. And that's really just a setup for it. And if I go ahead and do this out, it'll give me some volume answer. Now today what I'm going to do, I'm going to slowly shift this. I'm going to change my axis of rotation. Instead of being the x-axis, we're going to change it. Let's draw the parabola again, x squared. And we're going to go from 0 to 1. 0 to 1. But this time, instead of spinning it around the x-axis like we did before, we spun around this axis here. I'm going to shift it to make it a little bit lower. I'm going to shift it to be, let's say, -2. So I want you guys to get a visual of this. When I shift it around -2, as I spin it around, now what happens here is that the radius has now changed. The radius has now changed. Before, the r was described as just from the x-axis to the function. That was my r. But now we've extended that down. So my radius is actually from here to here now. So we actually have an easy way to figure out what my new radius is. And we use upper minus lower, or top minus bottom. Upper minus lower. And this is our radius idea. So we take the upper function, which is x squared, and my lower function, which is -2. And if you look at what does the math do, it makes the negative here into a positive. So it ends up, instead of subtracting 2, we're actually adding 2 spaces. And now if we look at it, all the function values are 2 spaces longer because the radius was extended by 2 spaces here. Now, does this always work? And the answer is, as long as we stick to upper minus lower, yes, it will. On the side here, if I give you another problem, let's use y is equal to the square root of x. Let's draw that out. What if I want to rotate this around the x-axis? Oh, sorry, not the x-axis, I'm sorry. Y is equal to, let's do -2 here again, -2. The radius would go from the function all the way down to -2. So our radius would be the square root of x minus a -2. And those negative signs become a positive. So our function becomes 2 spaces longer. Our radius becomes 2 spaces longer. Now what if I switch the position of my axis of rotation and I put it on top? Well, let's go ahead and take a look at that. Let's do the same problem. Let's do x squared again. Y is equal to x squared about y is equal to, let's say positive, let's do positive 1. Let's do positive 1. So for this graph here, we have our parabola. And at 1, just to let you know, the y value is 1, right? Okay. Oops. Our y value is 1 here. Our y value is 1. And what if I want to rotate around this axis here, up here? So this would be rotating this way, going upwards, right? In this fashion here, and going this way. So we follow our rule. Our rule was upper minus lower. In this case, the upper portion here would be the top, and the lower portion would be the function. So we would say the top is y equals to 1 minus the lower would be x squared. Now, does that really work? I want us to experiment with some values here. If x was 0, what would the radius be right here? The radius would be 1 minus 0, which is 0. If I moved over to another point, maybe 0.5, 1 minus 0.5 squared would be 0.25, and that would give me the radius, what's left over. And this continues forward. So the radius function is just the upper minus lower, and that'll be the case all the time. So in our problem here, that set up the volume equation from 0 to 1 will be pi 0 to 1 of r squared. What is my r squared here? My r squared is going to be 1 minus x squared because it's upper minus the lower. And that would give me my radius. And then a little bit of dx. So as long as we stick to upper minus lower for functions that are rotating across, like vertically across the x-axis that direction, or horizontal axis, it's always going to be upper minus lower. But what if the function is asking me to rotate from, for instance, along the vertical axis? So let's try vertical axis. So if I write the function x equals to y squared, and we'll do this from 0 to 1. So y is between 0 and 1. This gives us a graph that looks like this, from 0 to 1. And we're going to spin it around this way. So we end up with a, whoops, not too big. We'll put the graph that comes out like this and spins out this way. Okay. So these are still circles, and we have to figure out which way the radius is. looking at the radius, is from the axis of rotation, which is x is 0, to my function. And in this case, we're going to write it from, the radius is from right to left. Right minus left. And the reason why we always choose right minus left is because right is the more positive number. It's the bigger number. And when we subtract a bigger number from a smaller number, we end up with a positive number still. And that's really the reason why. So we say right minus left. And in this case, the radius, the y on the right side, it'll be y squared minus our axis of rotation here, which is going to be x is equal to 0. So our radius here is just going to be y squared. So when we write the function, integral, so volume is pi, integral from 0 to 1, y squared, that's my radius. And in this case, since we're making slices going this way, right, that's a little bit of dy. Little tiny slices of dy. I forgot to put here that it's going to be, this is pi r squared, right? I forgot to write the squared here. Okay. So we always need the square of the radius. Now for our next example, we're going to spin around a different axis. X is equal to y squared again, same function, except I'm going to spin around the axis is going to be the axis is going to be x is equal to -2 here. So we're going to spin this graph, -2, and we have our function y squared, and we're going to spin around this axis over here. So if you can notice that the radius is actually now longer. Before it would stop at 0, now it's going to be even longer. So that makes the shape even longer. We end up with these values here. And we're going to spin it specifically only from, we'll give ourselves a boundary. We'll stop at 0 to 1 again. So let's talk about the radius, what the radius is now. The radius is right minus left, which is on my axis of rotation in this case. Right minus left. The right value is y squared. The left value is a -2. And as we saw before, the negatives become a positive. So that actually increased my radius, which is kind of what we did. We kind of dragged it out a little longer. And the function, the volume, is pi from 0 to 1 of r squared. And our r function is y squared plus 2 squared. And then y. Okay, what about if my axis of rotation is on the right side of my graph? Okay, so x equals to y squared. My axis is going to be x is equal to, that's a positive 3 now. Sure. So 1, 2, 3. We have a parabola being drawn, or, sideways parabola. And we're going to spin this along the right side here. Now, just like what we said before, we want to find the radius, and the radius is this distance from here to here. Because when I spin it, it's going to end up with this kind of like this bowl-looking thing, a contact lens actually looking thing. Right? So what is this radius here? What is that radius? Well, we said it's going to be right minus left. R is equal to 3 minus, and that function is going to be y squared. Okay, right minus left. So these are both x values, just to FYI. That's an x value, that's an x value, right? X equals to y squared. These are both x values. And when I subtract the x values, that gives me my radius in between. So that set up the integral. The integral, so volume is pi r squared. We said from 0 to 1, right? From 0 to 1, whatever this value 1 is. And we are going to say that what's the radius squared? And the radius here is going to be 3 minus y squared, with a little bit of dy attached to it, because we want little layers, little thicknesses. I'm also going to include today in the YouTube link, there is a resource. If you guys want to see these things being spun out, there is a Wolfram Alpha app that you guys can spin things out, and you can see what they would look like in this 3D model. So you guys don't have to really draw it out, but you can see what they look like. Okay, and that's it for spinning volumes. Thank you.